Hi, my name is Manish Gupta, and in this video, I'm going to talk about this new model, Solar 10.7 billion. Okay, it actually uses this interesting technique called as depth upscaling. So we'll also talk about this technique as well in this video. Okay, so why does Solar 10.7 billion matter? So why is this model important? Well, this model is important because of the kind of results that you see in this table, right? So what do you see in this table? Well, there are results shown for 6 different data sets. So ARC, HelaSwag, MMLU, Truthful-QA, Vinogrand, GSM-8K, right? Very popular benchmark data sets for reasoning, for language understanding, for measuring bias and toxicity, for mathematical understanding, and so on. Okay. And then you also see results H6, which is basically average of the values that you see in the next 6 columns. Okay. Now, what you also see on the rows are different models being compared. So Solar 10.7 billion instruct, Solar 10.7 billion, which are basically proposed in this work. So it's basically Solar models. And then you see they being compared with the best of the models which are available as of today, right? I mean, essentially in 2024, what you have, the best ones right now are Mistral 7 billion instruct. You have the mixture of experts based Mistral, 8 cross 7 billion, right? And then you also have the recent models like Yi and Quen, right? Now notice the size of these models. So of course you have Falcon, which is 180 billion parameters. So I won't call it like a small language model, but you have Falcon as well being compared here. While Mistral, of course, Mistral Instruct, they are both 7 billion parameter models. While Mistral 8 cross 7 billion, of course, is a 47 billion parameter model, but leading to 13 billion parameters at inference time because it's a mixture of experts, right? Choosing 2 experts at a time. Okay, so now what you observe is that across all of these models, Solar 10.7 billion instruct is like really the best, right? So it basically gives you really good accuracy values or H6 average values across several of these models. So in fact, what you observe is that the non-instruction tuning-based Solar 10.7 billion is better than Quen and Mistral 7 billion, right? So it's better than its 14 billion sized model, another 14 billion sized model, and better than 7 billion. 66.04 is actually better than those, right? And then if you really look at the Solar 10.7 billion instruct model, well, it's best. So essentially, it's better than, in fact, even the mixture of experts based model. Now, the interesting part is that it's not just the best, but it's also simple. So why simple? Because if you consider mixture of experts model, it basically requires special handling while inference and even while training, right? While training, you need very large infrastructure because it has like 8 experts in it. So overall, like a size of 47 billion, right? At inference time, of course, again, you have to deploy all of those, and then you have to ensure that 2 of them are called at a time and so on. So 2 of the experts are being used at a time and so on. So basically, even the optimizations that you would do for inference, etc., are going to be very different from typical Llama kind of models. But Solar, interestingly, has no change in architecture, which basically makes it simpler to train and infer as well. So that is why Solar is important. Now, how is Solar trained? Well, Solar is trained using a technique called as depth upscaling. Okay, so and which is what I'm going to talk about on this slide. It's a very simple technique, super simple technique. Okay, so you start with a 32-layer Llama 2 architecture, which has been initialized with Mistral 7 billion because Mistral 7 billion has been the best so far. So therefore, what you do is to basically take Mistral 7 billion, 32-layer Mistral 7 billion model, which is basically a Llama 2 architecture, right? So you take that model, you copy it. So you basically have like 2 Mistral 7 billion models. Now, from this 32-layer model, you essentially retain the last 24 layers and get rid of these 8 layers. Okay. Similarly, from the second copy, you basically get rid of these 8 layers and keep these 24, right? So essentially, here you're going to keep these first 24 and these 24, and you're going to merge it. So that's basically the depth-wise scaling part. What is the depth-wise scaling part? Well, you take 2 copies of, or rather, you take two checkpoints of Mistral 7 billion, and then from that, you take from one of them, you take the first 24, the other one, you take the last 24. You merge them and you basically get a 48-layer model. Okay. So that's how that's how the Solar 48 layer 10.7 billion parameter model has been created. And then that's not enough. So basically, because of course there is a gap at the seam, so essentially there's a semantic gap in that senses. And to be able to make up for that gap, you have to do continued pre-training, so as to get the final Solar model. Okay. Now, of course, if you basically just do this stage, basically depth-wise scaling, then performance drops. But then after continued pre-training, the performance gets regained very quickly. Okay. So overall, how is Solar trained? Well, unlike mixture of experts, no complex changes to train or inference. Absolutely no complex changes. And it has like 3 stages of training. One is depth-wise depth of scaling. So where you do depth-wise scaling and then continued pre-training. And then after the pre-training is done, you do 2 steps of tuning. So essentially instruction tuning and alignment tuning. So it's interesting. So, they basically not just do instruction tuning like typically people do when they come up with instruction tuned models, but they also do alignment tuning. Now, that's an interesting concept by itself. So let's talk about that. So in instruction tuning, they do the typical stuff. They essentially use question answering formatted data, and they actually do instruction tuning, follow instructions. Okay. So in fact, they use 3 different kinds of data sets for instruction tuning: Alpaca GPT-4, OpenORCA, and synthetic math instruct dataset. Okay. So Alpaca GPT-4 and OpenORCA are already available public open dataset. Synthetic math instruct dataset, they basically synthesize themselves. Okay. They create themselves. So they have some, this is, as you observe, the number of samples are pretty small that are being used, 52K, 100K, and so on. OpenORCA comes from the same ORCA paper. So essentially, this is the ORCA dataset. This is from the ORCA guys, right? And then you have a synthetic math instruct dataset, 52K. So overall, the size of this instruction tuning dataset is about 204K, which is not large. It's not too large. Okay. It's not clearly as large as what OpenORCA folks or ORCA basically used. Remember, ORCA basically used 5 million samples from ChatGPT and 1 million samples from GPT-4. Okay. But these guys just use 204K. So instruction tuning is actually not as highly scaled. Okay. So that's that. Now, on the other hand, they also do alignment tuning. And what is alignment tuning? After instruction tuning is done, they basically want to align more with human or GPT-4 preferences. Using direct preference optimization. So DPO is a very recent technique which has been sort of considered as a replacement for reinforcement learning algorithms. So it's not a reinforcement learning algorithm, but it has been shown to perform as good while avoiding the difficulties while using reinforcement learning algorithms in terms of hyperparameter tuning and so on. Okay. So DPO requires direct preference data. So, preference data meaning you need data in this format. So there needs to be a prompt, and then there needs to be a chosen response and a rejected response, right? So essentially, basically saying that chosen response is preferred by the oracle compared to the rejected response, and that is what the model should learn. Okay. So now for their alignment tuning, the Solar folks basically use, they basically have a QA pair, right? They pass the QA pair to GPT-4. And then they basically get a rephrased question and a rephrased answer. So both of them are rephrased. Okay. So they use the rephrased question as the prompt, okay, assuming that the rephrased question is a better question, right? And they use the rephrased answer as the chosen response, and they use the original answer as the rejected response. So if GPT-4 sort of rephrase some answer, clearly it would have believed the original answer was not that great. So therefore, they use the rephrased answer as the chosen one and the original answer as the rejected one. Okay. Now, this kind of alignment tuning kind of stuff, or rather this way of generating alignment tuning data, they basically do it on 3 different data sets: ORCA DPO pairs, ultra feedback clean, and synthesized math alignment data set. Okay. So of course, these synthesized data sets are their own data sets, but ORCA DPO pairs, ultra feedback clean is basically just derived from the existing data sets. Okay. Now, again, if you observe the overall size that they sampled, the overall size that they make use of for alignment tuning is not very large. Just a few, less than 100K pairs, basically. Less than 100K such DPO triples. Okay. So that's that. In summary, why is Solar important? Solar is important because Solar 10.7 billion parameter model, it's not too large. It's 10.7 billion parameter model is better than Llama 2 and Mistral 7 billion model as well. Yeah. The instruct model, the Solar 10.7 billion instruct model, is actually better than Mistral 7 billion instruct, and also better than the Mistral's MOE-based 7 billion cross 8 model. Okay. It basically makes use of these three things: depth up scaling, so which basically involves depth-wise scaling and continued pre-training. The second is instruction tuning, and the third is alignment tuning. Alignment tuning, right? They also actually experimented with something called as model merging. So model merging has become a popular trend these days, where you take two different models, let's say two llama checkpoints, and if both of them are doing really well, you try to merge their weights. Now, literally merging weights here really means, just taking average of those weights or doing some such fancy stuff. Yeah. Of course, there are more techniques to do more fancy stuff about model merging. They tried model merging, but did not really see any conclusive gains. Okay. So therefore, the final technique essentially just consists of these three things: depth upscaling, instruction tuning, and alignment tuning. Okay, so that's it about the Solar model. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.